Okay, guys, we're gonna do Kirchhoff's rules. I understand that you did this last year in AP Physics 1. So this mostly will be a review, but then at the end of this video, I'm going to show you a simple way to solve a system of equations using a matrix. So I think you'll enjoy the end of this video and how to simplify some of those systems of equations. Okay? So in terms of the review from last year, we know that Kirchhoff's rules are the junction and the loop rule. The junction rule simply is due to conservation of charge. Okay, we know that in a closed circuit, as charge comes out of the battery, the same amount of charge that comes out of the battery has to return to the negative side of the battery, right? We don't lose charges in our circuit, and this is a conservation law that we're not going to lose charges in our circuit. We will at times use energy in things like resistors and light bulbs are going to use up energy of the charges. They don't actually delete any charges from the system. Okay, the charges just return to the battery with less energy than they had when they came out of the battery. Okay, so for Kirchhoff's junction rule, and due to the conservation of charge, it says that at any junction, okay, the current coming into the junction has to equal the current coming out of the junction. Okay, so we can't have, for example, if we have a junction which is wires in a closed circuit that are coming together, if we had 3 wires that came together at this junction, we couldn't see something like current coming in from all 3 directions. This would be an impossible situation where you have current coming in and then it just sits there on the junction and doesn't have anywhere to go. That wouldn't be the case for a closed circuit. So we would need to see something like maybe 2 currents are coming into the circuit and 1 current is going out. So maybe this is something like I1, I2, and I3. And what this allows us to do is it says that if I1 and I2 are coming into the circuit, then we would add them together, and they must be equal to the magnitude of charge coming out, or the magnitude of current coming out of the junction, so that is I3. And that's how we would write an equation for the junction rule, and again, it's due to conservation of charge. The next rule we have for Kirchhoff is the loop rule. It's also based on a conservation law, and this guy is conservation of energy. Okay, so it means that energy is still conserved in our closed loops in a circuit. We know that batteries are voltage sources, so what they're going to do is they're going to raise the potential energy of charges, and they're going to send them out into the system. And as charges encounter energy users like resistors and light bulbs and things of that nature, then they're going to lose some energy. Okay, and then they're going to return back to the battery with a certain amount of energy. And these are represented in the voltages that we would measure on the batteries and the resistors and light bulbs and such themselves. So the Kirchhoff loop rule says that the voltage around any closed loop. So if you look at any closed loop in a circuit, it doesn't even have to be a loop completely in the direction of the current. You can choose any closed loop in the circuit, and the voltage must add to 0. It must add up to 0. And again, this is to conserve energy in the system. That is, if we take a simple circuit with just 1 branch here, 1 loop, no junctions at all. Let me take a really simple one, which would just be a battery and a resistor. Okay. When I look at the battery, I look at the battery as a voltage source. It takes charges and it raises their energy up. So what I'm going to do here, I'm going to put the negative terminal of the battery is this side, the positive terminal of the battery is this side, and again, I consider the battery to be a raise in energy, a raise in voltage. It's providing energy to the charges. The charges will leave the battery in this direction. You'll notice here that I'm using conventional current. Conventional current means we look at we look at the charges coming out of the positive side and coming into the negative side. Mostly College Board agrees with using conventional current. The reason that I still use conventional current, even though we know that in real life the negatives are the charges that are actually moving, because it's easier to extract electrons because they're lighter and less bound to the molecules, we still use conventional current because it matches up with gravitational laws. And that is, in gravitational laws, we know that masses like to move spontaneously from higher potential energy to lower potential energy. And most of electrostatics and circuits have been built on the idea that positive charges will want to move from higher potential energy to lower potential energy. It's the reason why we did electric fields with positive test charges. We said, okay, draw the electric field as what would a positive want to do. And it's the reason why we still stick with conventional current, because it matches up with the same ideas and concepts of gravity. Okay, so I'm going to use conventional current here. I'm saying the current is coming out of the positive side. So this is my current. It's going to go through the resistor in this direction, and that's important. The direction that the current goes through the resistor is the way that the energy is going to be used up here. So that means that when I get to the resistor, I started on this end with higher potential energy. The resistor uses up some of the energy, and I will end up with a lower potential energy when the charges come out and return back to the battery. So I really like to put those negatives and positives here to show me how the energy is changing with each system element. Here the energy was a raise. Here the energy is a drop. It's losing some energy. This is really important because when you get to some very challenging circuits, you might have multiple batteries and you might have multiple resistors, and it is very possible that the circuit is so complex that you can have current going against the battery, going in the wrong direction as the battery is oriented, or you might go around a closed loop and there's no way for you to close the loop without accidentally going in the opposite direction of the current. In those particular cases, the resistors themselves are going to have to be treated as a raise in energy. So for example, what I want to do in order to do a Kirchhoff loop rule on this simple circuit, I want to choose a closed loop. And I only have one closed loop here, so this is a pretty simple one. And then I'm just going to choose a direction. Usually I try to choose the direction of the current. So I am going to do a clockwise loop right here. I'm going to do a clockwise loop. And very simply, then I'm going to take my finger and I'm going to go around this loop in a clockwise direction. And then when I reach a circuit element, I'm going to decide in the direction that I am moving my finger, is this a raise in energy or a drop in energy? So as I drag my finger up the battery, I go from the negative side of the battery to the positive side of the battery, so that is going to be a raise in voltage or a raise in energy, so that is via the battery, and I'm writing it as a positive. And then as I continue with my finger to go in a clockwise direction, when I reach the resistor, again, I know the current was going to be going this way, going down, so I called this the high energy side and this the low energy side. So when my finger goes in this direction, I'm going from high energy to low energy, so of course I know that this is a drop. So I'm going to write the voltage on the resistor as a minus. Okay, and we said that the voltage around any closed loop has to add up to 0, and that's to conserve energy. So the voltage raise of the battery minus the voltage drop of the resistor has to equal 0. And if we rearrange this equation, we could say that the battery's voltage has to be equal to the voltage on the resistor at all times. Okay. Now I said to you that there are times when the circuits get so challenging that you might be going in the wrong direction compared to the current that you chose. Okay, if I could maybe try to come up with an example that might make some sense to you. If I have, let's say, a really, really strong battery, say 90 volts, really, really strong battery. I've got a resistor here, and And I'm going to go ahead and give it a junction to make this a little bit more challenging. So let's say, for example, that I have here a resistor and here another battery. But this battery is really, really weak. It's only 1 volt, okay? So what I would want to do with this system is I would use both of Kirchhoff's rules, junction rule here because I have 2 junctions, as well as the loop rule, okay? But one thing that I need to do first is I need to establish the direction of current, and I could be wrong. When I guess, I'm taking a guess at the direction of current, and I could be wrong. The fortunate thing is when I solve this algebraically, if I've chosen the wrong direction of current, I'm just going to get a negative answer. And it's going to tell me that the direction that I chose was wrong, and I need to go back to the image and flip it. So what I'm going to do really simply is I'm going to say, I know the current is going to come out of this guy because it's so strong. And I'm going to put a plus and a minus here because we know that the battery raises the energy of the charges. And I'm going to do the same thing with the 1 volt battery. I know this is the positive terminal and this is the negative terminal. Okay, so current is going to come out of the 90 volt. It is going to go into the first junction. So I need to label this now as I1, and it is going to be split up at the junction. So I'm going to say because this 90 volt is so strong, there is not going to be any current coming in from the 1 volt battery. The 90 volt battery is going to force current in the direction opposite of the 1 volt battery. So let's give some labels here, R1 and R2. So I've got I1 coming in, it's going to split off into I2 and into I3, okay? So you'll notice here, I2 and I3, they're in a direction that it's going to make it impossible for me to choose a closed loop that goes in the direction of both I2 and I3. So that's why I said it was so important to label positives and negatives. Are resistors using energy in this direction, or are they going to actually gain energy in this direction? Well, I need to go to my resistors and label the high side and the low side, the high energy side and the low energy side. So if current is coming down this branch, then the resistor number R2 is going to use up energy in this direction. This is going to be the high energy side, this is going to be the low energy side. And the resistor R1, because the current is going this direction to the right, this will be the high energy side, and this will be the low energy side, okay? Now, for my loop, for my closed loop in this region right here on the left, this one is pretty simple. There is an obvious path where I can tell you what direction the current is going in. Okay, I1 goes this way, then this way, and then down this way is I3. I3 and I2 will return, but when I3 and I2 combine, of course, they make I1. So I1 is what will come back to the battery. Okay, and I can see with this current I1, I3, and I1, I can see that they go in a clockwise direction. So it's most obvious that I would want to choose a loop that is clockwise. And by choosing a loop that is clockwise, I'm always going to have my finger going in the direction of the current. So this is pretty simple. When I get to the battery, it is a raise of 90 volts. I go over and down. When I get to resistor 2, it is a drop because I'm going from the high energy side, moving my finger down. I'm going from the high energy side to the low energy side. So this is going to be a drop. But of course, voltage on resistors from Ohm's law is just IR. So here I'm going to be doing I3 times the resistor. Okay, and as I move back to the battery, I don't run into any other circuit elements. So in this closed loop, it's just the battery and it's just the resistor R2. And again, those have to add up to 0. Right? The voltages in any closed loop have to add up to 0. But it becomes a little bit more difficult when I consider this closed loop on the right. Because of this junction in I3 and I2 splitting in opposite directions, notice that whether I go counterclockwise is going to go against I2, and clockwise is going to go against I3. So really there is no good choice for the direction of my loop. So I'm going to choose one. I personally I personally like to choose the loop in the direction of the battery, the way that the battery itself is going. So what I'd like to do here is I would actually like to choose to go counterclockwise. Um, you could do this clockwise and it wouldn't be an issue. But again, just keeping in mind what direction are you moving across the positive and negative. So the reason I'm going counterclockwise is so that the voltage of this battery will be a raise. When I take my finger in a counterclockwise direction, when I go across the battery, I'm going from negative to positive, and that is going from lower energy to higher energy. So I get a raise of 1, okay? And I'm going to continue moving in a counterclockwise fashion, and I get to resistor 1. But you'll notice that resistor 1, when I'm going counterclockwise, I'm actually going against the direction that I had chosen the current, I2. So when I go through resistor 1, I'm going from the low energy side to the high energy side. So this actually, in this closed loop, needs to be considered an energy gain because I'm going backwards. I'm going counterclockwise. So that means that I have a gain of I2 times R1. This resistor is being treated as a gain because the direction of my loop is counterclockwise. Okay? And I'm going to continue on down through R2. And it says that R2, well, if I'm going counterclockwise, my finger is going down, and I'm going from the plus to the minus, so the high energy to the low energy. So that means, of course, in this direction, I'm losing energy, and I'm losing energy of I3 times R2. Okay? And these have to add up to 0, which we understand from Kirchhoff's loop rule. So you can say that 1 plus I2 times R1 is equal to I3 times R2. Now, I thought that was an important example just for you to see that there are times where resistors can look like a gain in energy. We know practically that in the direction the current is moving, the current energy of the current is being used up in this R1. But because I am going in a counterclockwise direction, I need to write this down in the loop rule as a raise in voltage. And that, again, that is just because of the direction that I chose. Here, I'm going counterclockwise. If I would have gone clockwise, then of course, this R2 would have been a gain in energy because I would be going from the negative to the plus side. This would be a drop in energy, and this would be a drop in energy. But in the end, I would end up with the exact same equation, and that is 1 plus I2 times R1 is equal to I3 times R2. Just to confirm that this is right, I think it's interesting to say from the first equation, I3 times R2 is 90. The voltage on this middle resistor is the same as the battery, and that makes sense because R2 is in parallel with the battery. R2 is in parallel with the battery. What also should make sense is that R1 and the 1-volt battery are in series, but notice, because of this junction, that they are also in parallel with the battery. So they should also have a total voltage of 90. And that's what we're seeing right here, that the voltage of the 1-volt battery and the R1 resistor together is equal to the voltage of the battery, which is 90. Because again, these are all in parallel. Okay? So I told you that I would show you a simple way to solve a system of equations. So here I have a little bit more challenging Kirchhoff example, but I would say that because there's only one battery, you do not have to do Kirchhoff here. So I'm choosing one that we already know the solution to or could find the solution pretty easily with an equivalent circuit. For example, because there's only one battery here, you could very simply do an equivalent circuit with the 3 and 5 ohm in parallel. You could say 1 over 3 plus 1 over 5 is equal to 1 over the equivalent resistance. So I would go to a calculator very simply, and I would say 1 over 3 plus 1 over 5, and I would inverse to find the equivalent resistance of 1.875. Now that is 3 and 5 in parallel are acting like a single resistor of 1.875 ohms. in series with a 2 ohm resistor. So in series with a 2 ohm resistor means the equivalent resistance of this circuit is 3.875. So this is the same thing as having a single resistor with your battery of 4 volts and a single resistor of 3.875 ohm. So the first thing I can do is I can figure out current, number one. What's coming out of the battery? Well, using Ohm's law and V equals IR, I can also say that I is equal to V over R. So that is 4 over 3.875. So current 1 is, we'll say 1.03 amps. Okay. I also know that if there's 1.03 amps going through the 2 ohm resistor, then the 2 ohm resistor would have a voltage of, using Ohm's law again, 2 times 1.03, it has a voltage of 2.06. Well, how much does that leave for voltage across these parallel terms? Well, you have a total voltage of 4. You've already used up 2.06 before getting to the junction. So it means the voltage on the 3 and the 5 ohm, which are in parallel, must be 1.94 because they have to add up, of course, to 4 volts. So if there is 1.94 volts on the 3 ohm resistor, then the current must be voltage divided by resistance. So 1.94 divided by 3 means that I2, the current in I2 is 0.647, and the current in I3, which again is voltage over resistance, is 1.94 divided by 3.388 is, sorry, 1.94 divided by 5 is 0.388. 0.388. Okay. And of course, we know there is a junction here. So the junction rule says that the current coming in, which is I1, must equal the current going out, which is I2 and I3. So I'm just going to confirm really quickly that 0.647 and 0.388, so 0.647 plus 0.388, do they add up? Very close. And again, we truncated and we rounded some things. So this is really close to the 1.03 amps that we said is coming into the junction. So we could of course gotten this answer using an equivalent circuit. But I like to start the matrix method with a problem that you already know the answer to, one that's pretty simple, just so you don't get bogged down by the details, you're comfortable with the answer that we get. Again, because this could have been done with an equivalent circuit just because there's only one battery. The moment that we get batteries in parallel, equivalent circuit is gone. It's not going to work anymore. As soon as you have batteries in parallel, you must do Kirchhoff's rules. This is the only way to solve these kinds of complex circuits. Okay. This one again, we solved it already, but I want to show you how I would do it with the matrix method. So I'm going to use the junction and the loop rule to come up with as many equations as possible, or as many equations as I need. So the first thing I'm going to consider is how many variables that I have. I've got I1, I2, and I3. Those are variables that need to be solved. So that means I have 3 variables. And according to the mathematicians, if you have 3 variables, you need 3 equations, right? Anything less, and it's mathematically impossible to solve. So if I have 3 variables, I need 3 equations. So what I'm going to do very simply is I'm going to start with the junctions. Start with the junctions. Now, the more complex this gets, the more junctions there's going to be. You want to do as many junctions as you can until they become redundant. That means go through as many junctions as you can until you write down a junction equation where none of the variables are new. That means if you already have an equation or several equations that involve all or any of the variables in a new equation that you try to write, that new equation is redundant. So the first equation I'm going to write, I'm going to look at the top junction. And it says that I1 is coming in and I2 and 3 are going out. So that means that I1 must equal the sum of I2 and I3. And then I'm going to go to the next junction. And again, I'm going to write down as many as I can until they become redundant. The second junction says that I2 and I3 come in to make I1. So I2 and I3 come in to make I1. So what I want to do now with this new equation is I want to check all previous equations. Has I2 been introduced in a previous equation? Yes. Has I3 been introduced in a previous equation? Yes. Has I1 been introduced in a previous equation? Of course it has right here. So this is what we would call a redundant equation, and this does not add anything new, so I need to eliminate it. Okay? If you don't eliminate it and you try to solve a system of equations with a redundant or with a redundancy, what you're going to end up with is something like, you know, if you're in a math class and you solve an equation, you get something like 0 equals 0 or 4 equals 4. It's because there was a redundancy somewhere, and it's because all solutions are possible for that redundant system of equations. So I need to drop this second equation. It's redundant. So now I'm out of junctions and I need to move to loops. Okay? Again, I need 3 equations. I only got 1 from my junctions, so that means I need to get 2 equations from my loops. So I see 2 pretty simple closed loops here. The left side and the right side. Of course, if you wanted to, you could also go all the way around the outside. That would be a third closed loop, but I only need 2. So I need to make sure that I don't, again, become redundant or oversimplify the system. So I've got I1 going up and I2 going down. It seems easiest to do a clockwise loop then. Again, I like to go in the direction of the battery so that the battery will be a gain in voltage, and I need to mark my positives and negatives here. Okay? So for my battery, I know this is the negative terminal and the positive terminal. The current is going through the 2 ohm resistor to the right, so this would be the high side and the low side. I2 is going down, so this would be my high energy side and my low energy side, and I3 is also going down, so here's my high side and my low side. Okay? So going clockwise in the left loop, when I get to the battery, it's a raise of 4 volts. When I get to the 2 ohm resistor, I'm going from the high side to the low side. So that's going to be a drop. And again, let's pretend that I don't know what I1 is yet. So the voltage here on the 2 ohm resistance is I times R. I1 times the resistance of 2 ohms. And as I go through the 3 ohm resistor, again, high side to low side, because I'm going clockwise, this is a drop. And this is a drop of 3 times I2. And all of the voltages have to add up to 0 in a closed loop. Let's do the next one, and you're going to notice here there's no good direction because there's no battery here, and regardless if I go clockwise or counterclockwise, I'm going to go against one of these. I'm either going to go against I2 or against I3. I'm just going to go ahead and choose to go counterclockwise. It's kind of a random choice, but I'm going to go counterclockwise. So when I go through the 5 ohm in a counterclockwise direction, I'm going from the low side to the high side. So that means the 5 ohm is actually going to be a raise. It's going to be a raise of 5 times I3. When I keep going counterclockwise and I go through the 3 ohm, because I'm going from the high side to the low side, this is going to be a drop of 3 times I2. And again, they have to add up to 0. So now I have a system of equations. A system of equations. What I'm going to do next is very simple. Move constant terms to the right. Move constant terms to the right side, and then line up variables vertically. Very simple. Move any constant terms to the right side and line up variables vertically. So in the 3 equations that I have, one is I1 is equal to I2 plus I3. The only constant term there is going to be a 0. If I move I2 and I3 to the left, then I have a 0 on the right. The second equation, I need to move the 4 over, and of course, I can subtract 4, but then I've got a minus on everything, so I'm going to go ahead and turn them all to positive, so it will be 2I1, 3I2, so 2I1 plus 3I2 is equal to 4, but the last thing I'm going to do here is I'm going to say plus 0I3. There is no I3 term in the second equation, but I want to line up the variables vertically. And the last equation, we have a 5I3, a minus 3I2 is equal to 0, so the constant term is 0. There is no I1 in this equation. Minus 3I2 and plus 5I3. So I've got all of my variables lined up vertically. I've got all of my constant terms lined up vertically. Very simply, to solve this equation, you could use substitution and elimination. Of course, you could go through this by hand. What I'm going to do is called the matrix method. Very simply, all of the algebra between these equations is going to be done for me in what's called a row reduced echelon form. Okay, I'm going to take only the coefficients of each variable and the constant term, and I'm going to put them into a matrix. So the coefficients of each of the variables. So coefficient of I1 is 1, 2, and 0. 1, 2, and 0. The coefficients of I2 are -1, +3, and -3. And then the coefficients on I3 are -1, 0, and 5. And lastly, I'm going to put the constant terms, which are 0, 4, and 0. Okay? And I'm going to put them into a matrix, and I'm going to ask the calculator to put this matrix into row reduced echelon form. And what that's going to do is it's going to play around algebraically with this matrix until it can make this matrix look like the following: 1, 1, 0, 0, 0, 1, 0, 0, 0, 1. So right down the diagonal right here, you should have ones right down the diagonal. This last column is going to be our answer for I1, I2, and I3. Remember that along the first column, these were our coefficients of I1, these were our coefficients of I2, and these were our coefficients of I3. So when we get our matrix in row reduced echelon form, we are going to have our answer for I1, I2, and I3. So how do you put this into a calculator? You've never done a matrix before, most likely. So you probably never even noticed that there is a matrix button on your calculator right here above inverse. So I'm going to go to matrix, and I'm going to go over to edit because I want to add a new matrix to my calculator. And I'm just going to add one to matrix A. So matrix A needs to have, well, it needs to have 3, 6, 9, it needs to have 12 numbers in it. And that is, it has 3 rows by 4 columns. So 3 by 4. And that gives us our 12 values. And right here we have a bunch of zeros ready to accept values into the matrix. So all I'm going to do is write down this matrix right here. So that is 1, -1, -1, 0, 2, 3, 0, and 4. 0, -3, 5, and 0. Okay, so that is now the matrix, and I've called it matrix A. What I want to do is I want to ask the calculator to put this matrix into row reduced echelon form, or we're going to ref it. So I'm going to go back to matrix, and this time I want to do math. I want to do math to my matrix, so I'm going to go all the way down here to where you see ref, and I'm going to hit enter. And when, oh, my apologies, I don't want to do that inside of matrix A. So again, matrix A, the last value here was a 0, enter, and I need to quit. I need to get outside of this matrix, okay? Just to check that nothing weird has happened, let me go and look at what matrix A is. 1, -1, -1, 0, 2, 3, 0, 4, 0, -3, 5, 0. So the matrix A looks good. I haven't messed anything up. Now I want to do some math to that matrix. So I go matrix, math, reref. Okay, and what matrix do I want to reref? Well, I want to reref matrix A. So let me go back to second matrix, and I just want matrix A. So I'm going to hit enter, and I'm going to close the parentheses. So it's going to row reduce echelon form matrix A. Hit enter, and you'll notice the last column is our currents, I1, I2, and I3. And that's exactly what we got when we did it using an equivalent circuit. 1.03, 0.64, 0.64, and 0.38. All right, so it's kind of an interesting way, especially when these systems get pretty difficult or you have many variables. The row reduced echelon form is a simple way to solve a system of equations. A system of linear equations can be solved with row reduced echelon form. Okay, so I'll put out one more video with a tougher Kirchhoff problem, and I'll do the matrix with you. So look forward to that one, and that's it for now.